So let's continue. Okay, look here. So this thing was obtained somehow from here. And here we consider the case where a functional J is of the form I sub h, where h is in P of W, and W is constructed by some function G in P star of U. We precisely need something like this here, because if you take J here equal to I sub h, we obtain precisely the functional which is mentioned here, lambda sub h. So lambda sub g is the following functional. When we put here I sub h, we obtain lambda sub h. Okay? So simply we write the same definition, but with h instead of g. Okay? So for such functions h, we have this inequality, and so we have this inequality for such function h. And what's about g? G here can be an arbitrary function which is symmetric, non-zero, and has support in this capital G. Okay, so for every symmetric G, this is true. Okay? And what I said means that, well, what can I erase this one? What I told means that H R of F includes P star of U R of F. Well, sure. Every symmetric G here satisfies this condition. So, okay. Now let's recall this upper bound. Let's recall the upper bound. And this means that if we okay. This means that if you take the following functional lambda r bar of f, this is simply the supremum by definition. Supremum lambda g of f for every g in h r of f. So this is finite. always find it because of this inequality. So we have obtained a new functional, which this time already doesn't depend on G. And in a way, it is even more nonlinear than the original functionals lambda J, because we have taken an additional supremum, so we have added some nonlinearity. But nonetheless, this means nothing. So what's about this functional? Clearly, it still remains homogeneous, of course. If I multiply by something, then and it is still left invariant because it is supremum of left invariant functionals. And it is positive. Okay. Now we claim the following, that for every test functions r to the power minus 1 lambda r bar f plus f prime is less than or equal to lambda r bar of f plus lambda r bar of f prime, and again it is less than or equal to r squared lambda r bar of the sum. So we claim that we have this inequality. So again, it is not very far from being additive.
Why here we have r squared?
Sorry?
Why here we have r squared?
Well, I will explain this. So this follows from some chain of inequalities which I have not shown you yet. But this is a claim. I'm going to prove this. But let's stop for a moment and let's look at this. So suppose we have proved this. Then when r tends to 0, it is clear that this r tends to 1. It's clear that monotonically, it's clear that this set becomes smaller. Yes? It's clear that set becomes smaller. The smaller r is, the smaller this set is. Yes? Because yes. It becomes smaller. So when we calculate this lambda r bar, it becomes smaller with r. Okay. So there is, and it is bounded. It is bounded. Okay. Anyway, it has a limit. It is monotonic, then it has a limit. And so from this inequality, it follows that this limit functional will be additive. Okay?
Yes. Wait, why is it always finite?
Sorry?
Why is it always finite?
Because of this.
And the problem is why the limit is not 0?
Что? Why it is not 0? At the very beginning, we proved some inequality with the norm and L infinity norm instead of J, which shows that this cannot be 0. Okay. Even if we take this limit lambda, we see that lambda of phi is equal to 1. Even so, this normalizing function phi, it is simply equal to 1, because here I phi of phi is equal to 1. And yes, even so, well, so it is non-zero on phi, and then it is non-zero on every non-zero function. So what remains is to prove this inequality. Okay. If you prove this, then everything is clear by simple linear procedure. And, well, you may remark that really we don't take any cluster point by Tikhonov theorem. Simply a limit exists. Well, we don't need to post some compactness arguments because simply a limit exists, and that's all. So in a sense, this is constructive because, well, if you know how to calculate the superemum, then it is constructive.
Yes, it makes me a little confused because
well, of course, it involves some finite coverings of compact sets, and you probably cannot do this constructively, but at least without axiom of choice.
in my mind that it use some axiom of choice.
No, it doesn't. It seems to me it doesn't. It doesn't.
Maybe all the proof I read.
It doesn't, because here the limit exists by monotonicity, and in the original construction by Weil. So this thing is called Haar measure, but Haar constructed it only for metrizable groups, and for general groups it was by Weil. And he used some cluster point and Tikhonov theorem. But then later it turned out that it did not require. So it was also very long ago, well, middle of 20th century. The adaptation which I am presenting is much more recent, but basically it is the same. Probably some details are arranged in a better way. I don't know, but basically it was known long ago, and the point is that simply a limit here exists, not because there is a cluster point, but a limit exists, and so this is an advantage of this proof. But in any case, to call this constructive involves some cheating, because constructive is not without axiom of choice. This is without third excluded. To argue without third excluded is something quite different. But anyway.
Why did you call it lambda bar?
Because we take the superemum here.
Yeah.
So lambda is this one. And lambda bar is something related to lambda, but we take a superemum with this lambda. So this is just a sign to denote this is a different object.
Okay. I just thought that if you use R is a number and not is a function.
I is a number.
So yeah, you could use. Okay, I understand.
I is a number. And well, this is monotone when R tends to. Okay. So we need to verify this inequality and then the length. Well. Okay. So take G in this set H O of F plus F prime. Then there exists a neighborhood W of unity, so that if H is in P of W, and I also must further restrict the range of this H So I want to ensure that this H be in HR of F and also in HR of F prime. So take some H in this set. And then we have the following. So R to the power minus 1 lambda G of F plus F prime is less than or equal to lambda H of F plus F prime. This is precisely this condition. You see? This is precisely this condition. And our lambda H is subadditive. So this is less than or equal to lambda H of F plus lambda H of F prime. And surely this is dominated by lambda R bar of F plus lambda R bar of F prime, because lambda bar is greater than lambda. Okay? So we have established this inequality, because passing to the superemum here, we obtained precisely lambda bar of. So to establish this inequality, it suffices to pass to the superemum over G here. Well, in the other direction, let now G belong to HR of F and G prime to HR of F prime. So consider two functions of this sort. It seems to me that I can erase this. Well, and here we need that superadditivity lemma. So there exists W, a neighborhood of unity. Such that if H belongs to P of W intersected with HR of F plus F prime, then we have the following. Lambda G of F plus lambda G prime of F prime. This is dominated by R lambda H of F plus lambda H of F prime. Here you see we have different G's here. And we have one of the same H here. We simply use this condition. This H serves all G's. Then we use that subadditivity lemma. Subadditivity lemma. This is dominated by R lambda H of F plus r squared lambda h of f plus f prime. So from another r comes from that subjective dilemma. You asked why do we have r squared here? Huh? You asked why do we have r squared here? So the second multiple r comes from that subjective dilemma. One from that condition, the other from the subjective dilemma, separative dilemma. Well, okay, and surely this is dominated by r squared times lambda bar r of f plus f prime, because simply this guy is greater than this one. Okay, and that's all. That's all. So we have proved this thing, and after the limit passage.
Yeah, excuse me, why do such h exist?
Such h, where?
I mean, why is the p of omega, the intersection with hr, is non-zero? Why is so?
Each time, all symmetric functions supported in a certain neighborhood satisfy the required conditions. Take a very small neighborhood, take a particular neighborhood for every condition, take the intersections, and every symmetric function in the intersection of these neighborhoods.
Okay, so it actually is just a p of a very, very small.
Yes. So we remarked here that this is, well, it is not clear why it happens so, but in this claim, which is still not quite clear, but the claim is that, so the claim itself is clear, but the proof is not clear still. But in this claim, it is said that every symmetric function, non-zero symmetric function supported on this U satisfies what we need. So take such U for every condition, then intersect them, then take any symmetric function. So we need to prove lemmas. We need to prove lemmas. Okay.
I'm sorry, where can I find such proof in some textbook?
It goes back to well, let me know. I don't remember how I found this text. Probably it was not published as a journal article, but it can be found on the internet. So just copy. But the first proof of this sort was due to Cartan, and this was in compte rendu sur la mesure d'art. Very long ago,
okay, thank you.
1940, and also probably in this book of Weil integration. There is an English translation and also a Russian translation. So Weil's book is classical. So I think there is something there, but maybe there is a proof with Tikhonov theorem. I don't know.
Want to. There are a lot of material used Tikhonov theorem, but
yes, but. Well, it seems to me that this article of Pedersen also contains a proof without axiom of choice, and well, the first one who guessed was Cartan.
Yes. Okay.
Probably here you can find something, and this will be quite the same I presented. Okay, but they are similar. All these proofs are similar somewhat. Okay.
One more question. If you formulated lemma 1 for a finite set of functions,
Yes.
but you use it only for two functions.
Well, I used only for two functions. Maybe it can be changed this way, I don't know, but the proof for two functions or finite number of functions is the same, so. So probably let's start with this lemma about superadditivity. It's lemma 2, yes?
It's lemma 1.
Lemma 1, okay. Let's start with lemma 1. But it will not be, the proof will not be direct somehow. It also will be with some reverse movement. Well, okay. Okay, let me recall what we need. So we have some functions, f1 and so on, fn, and we have r greater than 1. And we need the idea, the rough idea is as follows. So take f bar equal to this sum. Then fj is equal to rho j f bar, where rho j is equal to fj over f bar, and this is between 0 and 1. The problem is that if you do this, the function rho j is probably discontinuous, and so we are going to apply something like this to this function rho j, but this is applied only to continuous functions, and so this is some abstraction. To cope with this abstraction, we would like to, probably it would be good to somewhat increase this function f bar, take, instead of this sum, take something bigger, something strictly bigger. Something which is strictly positive, and then separate away from 0 on the support of this sum. Then all these functions will be continuous. So instead of f bar, you should take something bigger. Let's first do this. How to increase a function so that this increased function be strictly positive on the set where our initial function is non-zero. Yes, surely this can be done, and this is something like the Cantor theorem about equicontinuity.
Why can't you just add 1 to?
No. It must be with finite support, with compact support. In any case, so we must increase this, but to retain a compact support, and also we mustn't increase it too high, because we still need something like that. We still need some estimate of this sort. Okay. So for this, we need yet another lemma. Which is completely auxiliary. Okay. So lemma. Lemma 3, yes? Lemma 3 probably. It would be better to call it lemma 0, but anyway, lemma 3. So let f be a function with complex support and non-negative on our group G. Then there exists a row in the same space, so that it is strictly between 1 and 0, and the support of f is included in the interior of the set where this row is equal to 1. So my row is equal to 1 on the support of f, and even on some neighborhood of the support. So this is not about groups, of course. This is Jurson lemma.
Yes.
Yes, this is Jurson lemma. This is not about groups. So there are many such functions. So the first claim was that such function exists. Okay. And the second claim that if we have such a function, if rho is such, then there is a neighborhood of unity in our group G, such that we have the following inequalities. F of x is dominated by f of y plus epsilon rho of y, and this is dominated by f of y plus epsilon whenever x to the power minus 1y is in U, or y to the power minus 1x is in U. Okay, so this lemma, it is more or less clear that this is something of the sort of counter theorem about equicontinuity. So our group is not a metric space, but it is what is called a uniform space. Do you know what a uniform space is? Who doesn't know? Who doesn't know this term, uniform space? You know? Do you know? Well, I wonder if there is somebody who does not know this term, uniform space.
Would you mind?
Well, okay, you don't know. Well, anyway, I don't want to use the notion of a uniform space, but so in a metric space there is a notion of proximity of points whenever they lie. So they are close to each other if the distance between them is small, and they may lie at different positions in our space, but if the distance is small, they're close. In a topological group, this notion of proximity is expressed in the following way, that the quotient of these two elements must lie in a fixed neighborhood of unity. Since our group is not commutative, there are two types of such notion. Now, it is said here that if x and y are close, so you see, if rho is such, then there exists u. There exists a small measure of closeness. So if they are close, then f of x does not differ much from f of y plus something very small. So this is something like the Cantor theorem about technical continuity. And it is stated in this form because it will be used in this context. So I want to define this f bar in somewhat different way, and for this I need this auxiliary function rho and so on. Anyway, when we shall prove it, probably I shall use it first to prove lemma 1 and then prove it. But when we prove it, we can remark at once that we may not may avoid distinguishing between these two conditions because there is a base of symmetric neighborhoods of unity. So if we reduce our U to make it symmetric, then these two conditions are equivalent to notion of closeness. So okay.
Yeah. What are the pointers there?
So first, there are functions rho with these properties, and this is some topology. If rho is any such function, an arbitrary such function, then there is a neighborhood U of unity such that whenever x and y are 2 points in our group G which are close of order U, then we have this inequality.
No, the question is, what is the pointer between epsilon and U? Epsilon.
Fix an epsilon from the outset. So this U depends on epsilon, of course, as in the Cantor theorem, sure. Yes, I didn't, but so I thought so much about the Cantor theorem that so that I've explained already. But okay. So of course this U must depend on the epsilon. If epsilon is small, this U must be very small, and so on. Okay. Okay. And to apply, probably I'll postpone this till the very end because this is really something like the Cantor theorem. Very similar to the Cantor theorem, so not very interesting. But I'll do this, but later. And to construct some substitute for this majorant f bar, we need yet another lemma. Let me erase this. So lemma 4. Lemma 4. For every f in this space of twist functions, for every r strictly greater than 1, there is f bar also in the same space of test functions. And there is a neighborhood of unity such that first f bar is strictly greater than f on the closed support of f. So foreseeing the future, I tell that in this case, if we divide f by f bar, then we obtain a continuous function, what we could not obtain in this hint to the proof of lemma 1, which I gave you. So this is the first thing. And the second thing that, so this is A, B. F of x is less than or equal to f bar of y whenever x minus to the power minus 1y is in U, or y to the power minus 1 of x is in U. And third thing, g of f bar is dominated by r g of f for every functional g in our class f. So this f bar is slightly greater than f. Slightly means that all functionals in our class are only slightly greater than their values of f on this f bar. And moreover, this f bar has the following property. It is greater than f, but also if we change this x a little bit, so that these conditions, one of them is satisfied, then we have this inequality. So not only this one at every point, but also in some neighborhood of every point. And again, I remind you that these two conditions may be replaced by one if we consider symmetric Q. So let's prove this. Let's prove this. Not should be erased. Okay. It's not even needed anymore. Well, okay, if f is identical to 0, there is nothing to prove, of course. So we may assume that f is not identical to 0 without loss of generality, and take rho as in this lemma. But for this we should choose epsilon. And let us choose epsilon in such a way that 1 plus epsilon I f of rho, okay, is less than or equal to r. So we choose a rho with these properties, and then we choose small epsilon so that we have this inequality. Now take for f bar this function f plus epsilon rho. Well, it is strictly greater than f because rho is equal to 1 on the support of f. And even in the neighborhood of the support of f, so it is strictly greater. Okay. Then what else? Our functional j is subadditive and homogeneous, so j of f bar is less than or equal to j of f plus epsilon j of rho. For this j of rho, we use this fundamental estimate which we proved first. I don't write it out again, but simply know that this is dominated by g of f plus epsilon ef of rho g of f. So g of rho is dominated by this product. The very first inequality we proved from the definition of this functional. Yes? And now recall the choice of epsilon. And we see that this is less than or equal to r g of f. And that's all, because what else do we need? This one, but this one is clear from this inequality. You see? By this rho and this epsilon, we can find a neighborhood U so that we have this inequality. This is a triviality, of course, because rho is between 0 and 1, but we have this inequality, and this is precisely what is demanded here. Okay? And here we can we can make an important remark that if f was symmetric from the outset, it is invariant under inversion, then this f bar also can be chosen symmetric, because then rho can be chosen symmetric, and so on. Okay. This construction of this maximum, this gives from an arbitrary rho a symmetric rho, so, and this will be important. The SQL, you remember that in one of the lemmas, there was a requirement that some intermediate function be symmetric. It is not clear why this requirement was imposed right now, but we will see that it will be used in the proof simply. So it is important. Now, we have proved this lemma, and after that we can prove lemma 1. So lemma 1. So let f be equal to f1 plus and so on plus fn, and find some measurand f bar as in this lemma, more or less. So find such a majorant of bar, and here I put r to the power 1/2 for the reason of the argument. Then define rho j equal to fj over f bar, and this time these are continuous functions because of this. And moreover, the support of rho j is equal to the support of fj. Okay. Now we again apply this lemma, but not this lemma, but lemma 1 directly. Lemma 1, but not lemma 1, lemma 3, which was here on this blackboard. So this is something like the Cantor theorem, and even this is a statement which is much weaker than this lemma itself. So there is a neighborhood V of unity such that rho j of y is less than or equal to rho j of a plus epsilon whenever r to the power minus 1 y is in V. Rho j. This is much weaker than that lemma. Simply, this is something like the Cantor lemma proper. When we are not far from any point, no matter where this point is, and the function doesn't change very much. And here there is a finite number of functions, so each of them is uniformly continuous. Well, okay. So anyway, formally, this is a very, very particular case of that lemma which I raised. So once we used this lemma, and now we want to calculate what do we want to calculate? We want to calculate the functional Ig of f bar. I want to show that it is not very large. Okay, probably let me erase this lemma. It has already been proved, yes? So let me erase it. How to calculate it? By definition, we should consider such an inequality. So consider such a majorization and with some control of the coefficients. Now in this inequality, suppose that suppose we have at some point y, about y, we have some non-zero term here. Well, what does this mean? This means, in particular, that a to the power minus 1 y is in V, because this function g is supported on V. Yes? The function g is supported on V. Sorry?
Oh, yeah, so we take V as that.
Yes. I calculate this thing. To calculate this thing, so we take function g, calculate this thing. To calculate this thing, we should consider the following majorizations. We should try to find the smallest test for which this is true. And so let's consider such an inequality. Suppose it is true. Then, in fact, if we consider some point and some particular term, it is only interesting when this is greater than 0. If it is non-zero. And if it is non-zero, then we have the following thing, because our G is where? Where? Is supported on V.
Yeah, it's in the statement of dilemma. You didn't say that this V that you took for all the OJs should be taken as the V for the sum of F's.
So we have this, and this implies that rho g of y is dominated by rho g of a plus epsilon. Well, because we have chosen it in this way, where it is written here. Here. Well, and then we can write this thing, fj is equal to rho j f bar, and this is dominated by sum of r over r ca rho j g composition with LR to the power minus 1. Here we use this inequality. So here we have, when this is non-zero, the corresponding term is non-zero, we have rho j of y with this property. And then we replace this y, which is not written here, by a. So this is dominated by the sum over a in a, ca, rho g of a plus epsilon g composition with L a minus 1. So we have this majorization for fj with these coefficients. This means that ij of this fj is less than or equal to is less than or equal to the sum of these coefficients, okay? Well, now we sum this over G. Sorry.
Where is G?
G is with support in V. I forgot to say in the claim, in the statement of the lemma, G was in P of V. And V is this
where is G on the right hand side?
here.
It should be on the right hand side.
This is a number. This is a number. So we have such a majorization with G here. Then ij of this function doesn't exceed the sum of the coefficients. Okay. So there will be a double sum. And what we shall have here, plus like this, yes? Because when we sum over J, here we have epsilon times the number of summons. This is an epsilon, and here we have this sum. And this sum is less than or equal to 1. Why? Why is this less than or equal to 1? Yes, because yes, at every point, let's recall what rho j is. Rho j is this quotient, and f bar is greater than the sum of j. So the sum of rho j is less than or equal to 1. And finally, what do we obtain? We obtain the inequality, the sum over j of ij of fj is less than or equal to 1 plus n epsilon sum of a in capital A CA, and this is 1 to the power 1/2 times S, because our sum of CA was dominated by S. And when we take the infimum over S, then we obtain that this sum bar. Okay? But finally, we should obtain an estimate in terms of f rather than f bar, but we have another estimate of the sort we need. So this thing differs from this thing not very high. And that's all. So we have proved lab 1. We simply demand that this be smaller than r to the power 1/2. Yes. So epsilon is taken so small that 1 plus n epsilon.
And then we take V.
Then we take V. And then we take G with supporting V and so on. I told that this is not quite pleasant. Still, it's simple but not quite pleasant. Yes, well, but nothing terrible anyway. Nothing terrible. No complicated estimates. No analysis, if you want. No single integrals. But still not quite pleasant. At least you see that I don't remember this by heart. Well, okay, what should we do next? We need to prove this lemma 2 probably. We need to prove this lemma 2 and then lemma 4, yes. What's about lemma 2? So I remind you that this is a partial converse to the very first basic inequality. Again, take a function f in this space, take r greater than 1, then there must exist some neighborhood of unity such that for every symmetric G, non-zero G supported in this neighborhood, there is another neighborhood, U, W, so that we have this inequality. And this inequality is valid in two cases. First, for every additive functional, and second, for every function of this form where H is non-zero and supported on W. Okay, yes? So, somewhat tricky statement. I mean that the sequence of quantifiers is not self-suggestive. Okay. Why do we require here that this function be symmetric? Simply without this, the proof doesn't work. So here we must take only symmetric functions, must restrict ourselves to symmetric functions, because otherwise the argument will not work. You will see right now. Okay? To prove this, we again take a measurand for f. There exists f bar in this. Now I even can forget about the requirement that it should be strictly greater than f on the support of f, but the other requirement is very important. So there is f bar and there is a neighborhood of unity. Such that f of a is dominated by f bar of y whenever x to the power minus 1y is in U, and moreover g of f bar does not differ much from g of f. And this is true for every g in our class f of subadditive functions.
Should be a instead of x there,
Where?
right?
X. Sure.
Oh, this would be okay.
Sure. So this is again that lemma which I proved, or proved modular lemma Fortin, well, modular the Cantor theorem in the symmetrical groups. And now, as it is prescribed, let's take a symmetric G in P of U. Take G in P star of U. Then, again, by Cantor type theorem, formally by some weaker version of that lemma 4, which I will have no time to prove today, there exists a neighborhood V of unity, so that G of x to the power minus 1 y is dominated by I forgot. And there exists G bar, which is greater than G. Again, we take a majorant. Again, that lemma plays some role. So this is dominated by G bar of x to the power minus 1a whenever let me write this way: x to the power minus 1a to the power minus 1, x to the power minus 1 y is in V. Okay? So this is a formal application of that lemma, about the majorant, but let's observe that this thing is equal to a to the power minus 1 y. So this simplifies. So whenever these points are V close to each other, then we have this inequality. Okay? And moreover, G of G of G bar is dominated by, okay, what do we need here? Probably again r to the power 1/2 J of G. So this majorant is not much greater than G, but it satisfies this inequality. Okay. So we have used this majorization lemma twice. Next, we can claim that there exists some finite set A in G such that the support of F bar is included in the union of shifts of V. So V is a neighborhood when we consider all subshifts, such shifts by all vectors in A. Of course, they cover the compact set support of F bar, and then since it is compact, a finite subset of them covers the support, so this is compactness, nothing else. Okay. And after that, so we have an open covering of a compact set, and so there is a partition of unity subordinated to this covering. Should I explain what is that? No. So when we use this partition of unity, we can split our function f bar into the summons f bar a. This is not shift. This is simply means that the support of f bar a is included in a, just by partition of unity. Okay. Now I claim the following inequality for every x and y in G. It turns out that we have the following. If we multiply f of x times g of x minus to the power minus 1y, then this is dominated by the sum of a over a in capital A, f bar a of y, g of x minus 1y. And again, this is dominated by the sum over a, again in capital A, f bar a of y, g bar of a minus to the power minus 1x. So I want to explain how one can prove this. So the first inequality, of course, we may verify it only for those points for which this thing is positive. If this is 0, then there is nothing to prove. So I claimed some inequality. I want to explain why it is true.
I'm sorry, the left is fx or fy?
Well, where? X, y, and g, and so we have this inequality. This is fa of y. Here we have x, here we have y. Well, and here we have this, and here we have a to the power minus y minus 1x. So as it is written, precisely. Precisely. Now, why is this so? Of course, we may assume that this factor is positive, because if it is 0, then there is nothing to prove here. And if this is positive, so what's about our function g? G is supported in this, which one? Yes, in U. In U. G is supported in U. And so this means that in particular, this thing x minus to the power minus 1y is in U. And this means that f of x is dominated by f of y. And in fact, yes, because this is splitting by partition of unity, we have this. So we can replace this by here f of x by f of y. Okay, and now here what do we do here? We replace here this thing by this thing. So y becomes constant, and the order of factors is changed. So here we had x to the power minus 1 first, and then y, and here we have some constant in place of y, but as the first place, and x is as the second place, okay? Simply we estimate this term-wise. We estimate one term of this sort by the corresponding term of this sort. And this should be done only for those y for which this is positive. Because if this is 0, then the corresponding majorization is trivially true. So we suppose that this is positive. And then we look here. And we see that we can replace this thing with this thing. Okay? So we obtain nearly what is written here, but with somewhat different order of powers and of factors. But my function g bar is symmetric, and so I can change it for this. Sure. This is a place where it is important that g is symmetric. G bar is symmetric. Well, and here it should be r to the power 1/3, not 1 half, but 1/3. Now, again, by some of the preceding lemmas, there is a neighborhood W of unity, so that the sum over A EH of F R bar is then equal to r to the power 1/3 EH of F bar for every H in P of W. So this is superadditivity lemma, lemma 1. Okay? Sorry?
Maybe you will need power 1/3 plus.
Yes, 1/3 also, 1/3 also. 1/3 also. If we want to obtain precisely R, then it should be 1/3. Now this is superadditivity, lemma 1. If we take a small neighborhood, then okay. Okay. And now, okay, now we recall that we should deal with some functional g, which is either additive or of the form IH with H in P of W, like here. Well, in any case, let's apply this functional to this inequality, and here we fix x and consider this as a function of y. So we view this as a function of y and apply g to this inequality. What happens? So f of x g of G. In any case, J is a left invariant, so here this multiplication by x to the power minus 1 disappears. Is less than or equal to the sum of okay. So this is precisely, this is for the time being, this is subjectivity and nothing more. Yes? So we use this inequality and we obtain this. And after that, let's apply the functional ij in x. Well, what does it follow? What does it follow? Let me erase this, but we need this, but let me erase that. So ij of f, g of j is less than or equal to the sum over a in capital A, g of f a bar, I g of g bar, and here we can write this, can eliminate this by the following sum. Here, if we replace g bar by g, then we may save the situation by putting the constant of r to the power 1/3. And this is 1. Gj of j is 1 because j covers itself without any shifts and so on. This is 1. So. And now what does it remain? It remains, consider two cases. First, where this functional j is additive. And then the sum is simply equal to g of f. Yes? If it is additive, then the sum of fa is f.
What is fa
without a bar. Bar. This is j of f bar, yes? This is j of f bar, simply. But if it is of this form, then by this superadditivity lemma, this is dominated by r to the power 1/3 again this j of f bar. Yes? So in any case, we obtain what we need, and 3 times r to the power 1/3. When it is multiplied, we obtain r, and so on. So,
one small question: why is EGG 1? Why couldn't it be smaller than 1?
Because yes, it may be smaller than 1, but I write.
You just said that it's exactly 1.
Yes, not quite. Doesn't exceed 1. This is evident. Maybe it is smaller than 1. I don't know. Okay. So I have proved everything except the version of the Cantor theorem, and We will prove this next time and then switch to something else, to applications of hard mesh.